It's easy to forget just how fast things changed. 2 years ago, when we talked about distant galaxies, most of what we said came with a giant asterisk. We thought we saw the first stars forming. We believed we had an idea of what early galaxies looked like, and when it came to alien planets, we were basically guessing, tracing shadows, and hoping for the best. Then James Webb opened its eyes and suddenly the asterisks started disappearing. We weren't just detecting planets anymore. We were finding actual signs of what might be in their atmospheres. We weren't squinting at blurry dots from 13 billion years ago. We were looking at fully formed galaxies. According to everything we thought we knew, shouldn't have even existed yet. And that was just in the first few months. Since then, James Webb has rewritten our understanding of the universe, one target at a time. From ghost galaxies that stopped forming stars billions of years before they were supposed to chemicals in exoplanet skies that don't belong there. If you were hoping for a telescope that would quietly confirm what we already believed, this is it. So let's look back not at the launch, the hype, but at the work, the timeline, the things it actually found moment by moment, because the real story of Webb isn't in its design, it's in the discoveries, and some of them still don't make sense. The journey toward understanding the deep universe through Webb's lens, what many are calling the most important single image in modern astronomy. We all saw that first deep field image, and it looked like a starry wallpaper, nothing more than a tiny dot in the sky, magnified 100 times over. But once the shock wore off and people stopped saying pretty, the scientists started digging into the details. And that's when things got interesting. That single image, just one, showed thousands of galaxies. Not stars, not planets, galaxies. Each one filled with billions of stars of its own scattered across an area the size of a grain of sand held at arm's length. It was called SMACS 017T3, a massive galaxy cluster, 4.6 billion years away in the constellation Volans. But honestly, the name didn't matter. What mattered was what it proved. For the first time, we had a clear infrared look into the deep universe. And it didn't just show distant galaxies. It showed warped light, lensed arcs, ghostly shapes stretched across space and time. That warping wasn't an error. Massive clusters in the foreground were bending the light of even more distant galaxies behind them. And those distortions weren't just beautiful, they were useful. Gravitational lensing acts like a natural telescope. It magnifies. It reveals. It lets us behind the curtain at things we could never see with conventional means. So in that first image, we were already looking at galaxies that existed over 13 billion years ago. Just a few million years after the Big Bang, that alone was impressive. Here's the part that caught everyone off guard. Some of those galaxies looked too bright, too structured, too evolved, and that didn't line up. According to most models, galaxies back then were supposed to be small, chaotic, and still forming their first stars. But what Webb showed, even that first photo, was something that looked much further along. Smooth structures, defined clusters, evidence of star formation that should have taken hundreds of years, more than the universe had given them at that point. So naturally, the questions started piling up. Were these galaxies forming faster than we thought possible? Were our models of the early universe just wrong? Or were we looking at something else entirely, a different kind of structure built under different rules? And this was just day one. Before Webb had even locked in its full calibration, before its instruments had been tested across the board, it had already sent us to the drawing board. Not because the data was unclear, but because it was too clear. It didn't confirm our expectations. It challenged them. What's wild is that this wasn't some deep survey that took to complete. It was a snapshot, a glimpse, proof that even in the blank parts of the sky, there are entire universes hidden in the dark, waiting, quiet until the right lens came along. That lens was James Webb, and in just a few hours, it rewrote our map of the early cosmos. The implications of that first image rippled through the astronomical community in ways that are still unfolding years later. Theorists who had spent careers building models of galaxial formation found themselves questioning fundamental assumptions about how the universe works. The mathematics that had seemed so elegant, so well tested, suddenly are incomplete. It wasn't that the models were entirely wrong, but they were missing something crucial, some ingredient or process that allowed galaxies to mature far faster than conventional wisdom suggested. Some astronomers began proposing that star formation efficiency in the early universe might have been dramatically higher than in our current epoch. Others suggested that the density fluctuations in the early universe might have been more pronounced than our models of cosmic inflation predicted. Still others wondered if perhaps we were misinterpreting the redshifts, the cosmic distances themselves. But Webb's data was precise enough to rule out most of these easy explanations. The galaxies were there, and they were as massive and structured as the telescopes indicated. A telescope like Webb wasn't built just to stare into the ancient past. It was also designed to look closer, not at galaxies billions of light years away, but at stars just down the street, orbiting their own little worlds. Worlds we'd been chasing for years, guessing their shapes, estimating their temperatures, watching their shadows. And up until now, that's all we really had, shadows. When a planet passed in front of its star, we'd see a tiny dip in light. That's how we found them. That's how we measured them. It worked, but was limited. You can learn a lot from a silhouette, but it doesn't tell you what the planet is. It doesn't tell you what it's made of, or what's in its sky, or if anything's living there. Webb changed that. Its infrared sensitivity made it possible for the first time to read the actual chemical fingerprints of an exoplanet's atmosphere. Not indirectly, not through noise and modeling, but directly by splitting the light that passed through it and analyzing the spectrum one wavelength at a time. That's how we got the first clear carbon dioxide on a planet outside our solar system, WASP 39b, a hot giant 700 light-years away. That one single resolved the concept. It wasn't just hype anymore. Webb could read alien atmospheres. The ability to detect and analyze exoplanet atmospheres represents a fundamental shift in how we approach the study of distant worlds. For decades, finding exoplanets was the challenge. Astronomers developed increasingly sophisticated techniques to detect the subtle wobble of a star caused by an orbiting planet, or to measure the minute dimming of a star's light as a planet passed in front of it. These methods were remarkably successful, leading to the discovery of thousands of worlds in distant solar systems. But success in finding planets created a new problem, a new frontier. Finding them wasn't enough. Scientists wanted to know what they were. What were their atmospheres made of? Were they thick or thin? Did they contain any molecules that might suggest biological activity? Could life even exist in such environments? For years, these questions were largely theoretical, the domain of speculation and educated guesses. Webb changed that calculus entirely. The infrared wavelengths observes pass through planetary atmospheres more readily than visible light. And when they do, they leave chemical signatures. By carefully analyzing these signatures, astronomers could now determine what molecules were present in distant atmospheres with unprecedented precision. And then Webb went further. It found water vapor on WASP ABS, and GGG 4866b. These aren't planets. One's boiling, one's practically hugging its star. Another orbits so close to its star that the atmosphere should have been stripped away billions of years ago. But the point isn't that they could host life. The point is that we could read them, measure the thickness of their clouds, track changes in pressure, see signs of things like methane and sulfur dioxide, gases that mean something when they show up in the right combinations. These detections opened up entirely new avenues of research. Astronomers could now start to categorize exoplanet atmospheres, to look for patterns, to understand the chemistry occurring in these distant worlds. They could begin to ask more sophisticated questions about what drove atmospheric composition, what processes might be occurring in these alien skies. Then came WASP-17b, and that's where it got weird. Webb didn't just find vapor or gas. It found solid particles in the planet's sky. Tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water droplets. This planet was flinging microscopic quartz around like hail. It was the first time we'd seen anything like that. And it made us realize something fundamental. Exoplanets don't follow Earth's playbook. Their weather systems, their skies, their entire logic might be different. Wildly different. And Webb was the first tool that could actually show us. The discovery of silicate clouds 17 beings wasn't just interesting because it was unusual. It was transformative. It demonstrated that the diversity of planetary atmosphere and in the universe was far greater than most scientists had anticipated. If WASP-17b could have glass clouds, what else was out there? What other exotic atmospheric phenomena might exist on worlds circling distant stars? The quest formed from whether we could detect exoplanet atmospheres to what kinds of atmospheres were actually possible. And Webb was the instrument that could help us find out. But Webb didn't stop with exoplanets. Webb turned its gaze inward toward our own solar system. And even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune in over 30 years. Not just the rings, but the thermal profile, the poles, the cloud tops. The level of detail was unreal. Every swirl and storm in Neptune's atmosphere suddenly became visible in ways that previous telescopes simply couldn't achieve. Webb's infrared capabilities. It could penetrate Neptune's thick clouds and reveal the heat signatures of atmospheric phenomena, showing us a living, dynamic world rather than the static blue sphere we'd grown accustomed to seeing in textbooks. Then it locked onto Chariklo, a strange asteroid with its own tiny ring system, and detected water ice. That's an object only a few hundred kilometers wide. Yet Webb could map its surface composition with remarkable precision for a telescope that cost over $10 billion and was designed to look at the distant universe. The ability to study a small asteroid with such clarity seemed almost like a bonus feature. Yet it spoke volumes about the sheer power of Webb's instruments and its ability to observe vast ranges of scales and distances. Then it turned to Europa, one of Jupiter's moons, and detected plumes of water vapor venting into space. That confirmed what we suspected from older missions like Galileo and Hubble. But this time it was crystal clear. Europa wasn't just frozen, it was active, breathing, jetting out the contents of its subsurface ocean like a leaky faucet. And Webb was watching it happen in real time. The implications were profound. Europa has long been considered one of the most promising places in our solar system where life might exist, hidden beneath its icy crust in a global ocean. The detection of active water plumes meant that this subsurface ocean was accessible. That material from the interior was being ejected into space where robotic probes could potentially sample it. It meant that future missions to Europa suddenly seemed more promising, more achievable. The ocean beneath the ice wasn't just theoretical anymore. It was actively announcing itself to anyone with the right tools to listen. Even Comet 38pp read, a small rock in the asteroid belt, got its spotlight. Webb detected water, but no carbon dioxide, which was weird. Most comets have both. This one. That tells us that maybe this comet formed in a warmer we thought, or that its CO2 has long since escaped. Either way, that's a clue about comet formation, about solar system chemistry, about how water made its way here in the first place. The story of how water arrived on Earth remains one of the great mysteries of planetary science. Water is essential for life as we know it. Yet Earth's water content may not have originated here. It may have been delivered by asteroids and comets from the outer solar system in the early days of planetary formation. By studying the composition of comets and asteroids in our own solar system, astronomers can begin to understand the delivery mechanisms that brought water to Earth. Webb's ability to detect and analyze these objects, even small ones, provides new data that helps fill in the details of this ancient story. And then there were the trans-Neptunian objects, icy bodies, way out past Pluto. Webb started picking up traces of methanol and organic compounds on them, too, helping us piece together what the outer solar system was like in its earliest days. These weren't just static leftovers. They had chemistry, change, history. The outer solar system is often thought of as a frozen wasteland, a region devoid of interest or activity. But Webb's observations revealed a surprisingly rich chemical diversity in these distant objects. The presence of organic compounds and methanol suggested that complex chemistry was occurring even in these cold, seemingly inert bodies. It suggested that the processes that led to the emergence of life on Earth might not be unique to Earth, that the chemical building blocks of life were being created and distributed throughout the solar system. This realization had profound implications for how we think about the potential for life to emerge elsewhere in the universe. So yes, James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, whether it was a planet we'd already discovered or a moon we'd been circling decades, it showed us something we missed. The versatility of Webb was unexpected by some, yet, in retrospect, it makes perfect sense. An infrared telescope with such sensitivity and precision would naturally be useful across a wide range of distances and targets. What distinguished Webb wasn't just its ability to observe distant galaxies, but its ability to do so while also providing unprecedented detail of nearer objects. This combination meant that Webb could address questions across an enormous range of scales and distances, from the formation of the first galaxies to the composition of asteroids in our own cosmic neighborhood. In 2023, JWST started pouring in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies. It was picking up in the first few 100 million years after the Big Bang. Not just faint blobs of light, not background noise, fully formed galaxies, dozens and then hundreds in places we thought were still empty space. And some of them were just wrong. Take Sears 93316 for example. Based on its redshift, it looked like this galaxy existed just 235 million years after the Big Bang. the farthest galaxy ever observed at that point. That's way earlier than we expected anything that complex to exist. And it wasn't alone. Webb kept picking up more like it. Bright, compact, well-structured galaxies that didn't look like they were still forming. They looked done. And that was a problem because to make a galaxy like that, you need time. You need heavy elements. You need stars that live and die and explode and recycle their guts into the next generation. You need dust and gas and rotation and gravity, all working in sync over hundreds of millions of years. But these galaxies didn't have that kind of time. The cosmic timeline that astronomers had constructed over decades suddenly seemed inadequate. The Big Bang occurred approximately 13.8 billion years ago, and yet here were galaxies that appeared to be fully mature, just 235 million years into the universe's existence. That's roughly 1.7% of the current age of the universe. In that incredibly short time frame, these galaxies had apparently gone processes, according to conventional models, should have required 10 times longer. They had somehow managed to form stars, accumulate heavy elements, distribute those elements throughout their volumes, trigger supernovae, and organize themselves in coherent structures. The physics that allowed rapid evolution remained mysterious. Some theorists began proposing that the early universe might have been fundamentally different from the current universe in ways we hadn't previously appreciated. Perhaps the density fluctuations in the early cosmic web were more pronounced. Perhaps the efficiency of star formation was dramatically higher. Perhaps some unknown physics was at play. The bottom line was clear, though. Our models needed revision, so something wasn't adding up. Were these galaxies somehow forming faster than anything we'd ever seen? Were they forming differently, skipping steps we thought were necessary? Or was our timeline for the early universe off by a wide margin? These weren't just academic questions. They struck at the heart of how we understood the universe's history and the physical laws that governed it. If the early universe, according to fundamentally different principles than the current universe, that had profound implications for modern cosmology, if it operated according to the same principles, but just more efficiently, that suggested we've been underestimating star formation efficiency. Either way, understanding these ancient galaxies was crucial to understanding ourselves, because it was the first galaxies like these that eventually led to galaxies like the Milky Way, and ultimately to planets Earth and the emergence of life. And then Webb found something even stranger. The JWST Deep Extragalactic Survey, CHEDIS, one of its largest deep field imaging programs, focusing on the good SS and good SSN fields, offered detailed images of galaxies at high redshifts. These observations were expected to refine our understanding of galaxy formation and clarify how supermassive black holes achieve their enormous masses so early in cosmic history. However, a surprising discovery from JADA's data has challenged fundamental assumptions about the universe's structure. Specifically, the principle of isotropy, which posits the universe should appear roughly the same in all directions with no preferred orientation or spin. In a study led by Leo Shamir of Kansas State University, researchers analyzed 2663 spiral galaxies in the Good's South field using the G-analyzer algorithm, which assesses galaxy spin direction from radial intensity plots. The results revealed a striking asymmetry. 158 galaxies rotated clockwise, while 105, 40%, rotated counterclockwise. This imbalance hints at a possible preferred spin direction in the space, challenging the notion of a directionless homogeneous universe. The implications of this asymmetry, if confirmed by further observations, would be revolutionary. The cosmological principle, which states that the universe is homogeneous and isotropic on large scales, has been one of the foundational assumptions of modern cosmology. It's the principle that allows us to build predictive models of cosmic evolution. If there were preferred directions if the cosmos had some kind of overall spin or orientation, that would fundamentally alter our understanding of how the universe works. It might suggest large-scale structure and coherence on scales we previously imagined. Previous studies have noted similar spin asymmetries, with the effect appearing more pronounced at higher redshifts. Potential primordial structure in the cosmos. Some speculate this could align with physicist Nikodem Popowski's unconventional theory, which proposes our universe inside a rotating black hole in a parent universe, possibly imparting a directional spin bias to cosmic structures. It's an exotic idea, the kind of thing that most mainstream cosmologists would be hesitant to embrace without overwhelming evidence. It's the kind of idea that becomes worth taking seriously when observations like these keep cropping up. However, Shamir's team offers a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion could make galaxies spinning opposite to our perspective, clockwise from Earth, appear slightly brighter due to the blue shift, potentially skewing automated classifications. It's a more mundane explanation than invoking cosmological principles or parent universes, but it's also an important reminder that extraordinary claims require extraordinary evidence. The small sample size of 263 galaxies and the challenges of imaging high redshift objects further urge caution. Larger sets from ongoing JWST observations will be crucial to determine whether this asymmetry reflects a true cosmic phenomenon or an observational artifact. The important point, Webb is precise enough that it's revealing these subtle patterns at all. It's giving us the data to ask these questions. Whether the answers will require revolutionary physics or merely beta reduction techniques remains to be seen. Compounding these challenges to cosmological models, JADAS has also uncovered galaxies with redshifts exceeding 13, meaning they existed when the universe was less than 300 million years old. These galaxies, far from being weak protostructures, are luminous, compact, and surprisingly mature. A standout example, JADAS C is the with its extreme redshift, has forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such a short time frame. Typically, such collapses require extended periods. Yet these galaxies appear fully formed within the universe's first 300 million years. This is not an isolated anomaly, but part of a pattern. These early galaxies weren't just existing. They were thriving, actively forming stars at ridiculous rates. More stars than they should have been able to form with the limited ingredients available. Watching a campfire suddenly erupt into a 5-alarm blaze, but in the vacuum of space before the wood had even dried, the star formation rates in these ancient galaxies defied conventional explanation. Astronomers calculated that, given the amount of gas available and the known efficiency of star formation in the current universe, these galaxies should have been forming stars much more slowly. Yet here they were, blazing away like cosmic furnaces. Some astronomers started calling it the too early, too big problem. The galaxies were too massive, too luminous, too soon. And as Webb continued to observe, finding more and more examples of this phenomenon, it became clear that this wasn't a statistical quirk or a measurement error. It was a fundamental challenge to our models of cosmic evolution. So what's going on? One possibility is that star formation in the universe was simply more efficient than we thought. Maybe conditions back then, higher densities, more frequent collisions, allowed galaxies to grow at warp speed. Or maybe our models are missing some critical ingredient, a cooling mechanism, a gravitational effect, something we haven't accounted for yet. Theorists proposed mechanisms by which gas could cool more efficiently in the early universe, allowing it to collapse into stars more rapidly. Some suggested that the initial mass function, the distribution of stellar masses being formed, might have been skewed toward more massive stars in the early universe. Massive stars would form and burn out quickly, but they would produce heavy elements and energetic radiation that could drive further star formation. This kind of positive feedback could potentially accelerate the overall star formation process. Another idea is that these galaxies formed from direct collapse. Instead of slowly gathering stars and building up mass, maybe some of them collapsed almost instantly from dense gas clouds, forming stars and black holes in one quick chaotic event. If that's true, it could explain how some of the earliest quasars, the super bright beacons powered by black holes, came to exist so early too. The theory of direct collapse has long been speculative, but as observations of the early universe accumulated, it began to seem less like a fringe idea and more like a possible necessary component of a complete theory. Direct collapse would allow black holes to form on timescales that match the observations, without requiring intermediate populations to create them. It was an attractive explanation precisely because it was so extreme, so rapid. But here's the twist. The more we try to explain it, the more complicated it gets. Because every time Webb stares into those early epochs, it finds more galaxies, not fewer, not less, more structure when we expected randomness. And now astronomers are facing a deeper question. What if the early universe was never as quiet as we thought? What if everything, galaxies, came online faster and louder than we've ever imagined? If that's true, then the universe isn't just older than we thought. It's busier, more aggressive, more alive, even in its infancy. The philosophical implications of this realization are significant. For decades, astronomers had thought of the early universe as a quieter place, a place where structures slowly emerged from quantum fluctuations amplified by cosmic inflation. The universe's early epochs seemed almost peaceful in a cosmic sense. Structures formed gradually, galaxies emerged slowly from the darkness. But Webb's observations suggested a much more violent, much more active early universe. Stars formed in bursts, galaxies collided and merged, black holes fed ravenously. It was a cosmos in turmoil, a cosmos far from equilibrium. This vision of the early universe demanded new explanations, new physics, or at least deeper applications of existing physics to extreme conditions. And all of these findings that broke our timeline, they came from just the first year of Webb's deep fieldwork. We're only scratching the surface. The moment we found galaxies that were too big for their age, another question came up right behind it. If these galaxies are already so massive this early, where are the black holes that should have grown with them? That's been a long-standing puzzle in astronomy. We know most large galaxies today have a supermassive black hole at the center, sometimes billions of times heavier than our Sun, but we still don't know exactly how they form. Do they start as small ones that slowly eat their way up? Or do some just appear fully grown? James Webb didn't solve that question, But it gave us something we didn't expect: proof that these monsters were already around in the early universe. The relationship between black holes and galaxies has been one of the great mysteries of modern astrophysics. Observations over the past couple of decades have revealed a tight correlation between the mass of supermassive black holes at the centers of galaxies and the properties of those galaxies, particularly the velocity dispersion of stars in their central regions. This correlation suggests a deep connection, an intimate relationship between black hole growth and galaxy evolution. But the exact nature of this relationship remains unclear. Black holes shape galaxies. Do galaxies determine black hole properties? Probably both, in some complex feedback loop that we still don't fully understand. Webb's observations were beginning to provide new data that could help untangle this relationship. Yet they were also complicating the picture by showing that the black holes and galaxies were both much maturer in the early universe than expected. One of the biggest surprises came from a galaxy called Sears 119. It's distant, but when Webb looked closer, it saw a clear signal. The telltale signature of an active galactic nucleus, meaning there's a black hole in the center, and it's feeding, not just existing, not just waiting. That's important because Sears 119 isn't in the modern universe. It's from a time when the cosmos was only about 570 million years old. So how did a black hole, even a small one, form, grow, and start actively pulling in matter that early? That's not supposed to happen. Black holes need material. They need mass to form. They need stars to die. They need galaxies to evolve. And all of that takes time. But this one and a few others like it seemed to skip that timeline entirely. They're just there. That led researchers to revisit a controversial idea: direct collapse black holes. The idea is that instead of forming from stars, some black holes might form straight from massive clouds of gas, collapsing under their own weight before a single star ever shines. It's messy, it's fast, but it might explain how black holes could have been born big. And once they're big, they don't stay quiet. That's where quasars come in. Webb began spotting quasars, incredibly bright beacons powered by black holes, matter from more than 13 billion light-years away. These weren't subtle detections. These were objects so luminous that they were practically shouting across the universe. One of them in a gate 0439 us 16334, so distorted and amplified that could only be explained by gravitational lensing, a giant galaxy cluster bending the path of its light across space. That's not just a pretty trick. It's a window into the deep past. Lensing takes objects that would normally be too faint and stretches them out, magnifies them, gives us access to more detail than we should be able to get. The discovery of these early quasars was particularly puzzling to theorists. Quasars are powered by accretion of matter onto black holes, and they're incredibly luminous. An individual quasar can outshine an entire galaxy of hundreds of billions of stars. For a quasar to shine so brightly, its black hole must be enormous and actively feeding. Yet in the early universe, not enough time had passed for these conditions to develop through conventional processes. The existence of these ancient quasars, therefore, posed the same temperature challenge as the mature early galaxies. How could all this happen so fast? Once again, direct collapse black holes offered a potential answer. If black holes could form directly from collapsing gas clouds, reaching significant masses in remarkably short times, then powering a quasar would be possible even in the very early universe. And it works both ways. One of the most striking examples came in September 23, when astronomers spotted a supernova, a dying star that'd been triply lensed by a galaxy cluster. It was nicknamed SNSHP. It appeared in 3 places at once, all slightly offset in time. Think of it like a cosmic time delay. The same explosion playing back through different routes in space. That's more than just fascinating. Useful. By measuring how long each image takes to appear, astronomers can actually use lensed supernovae to measure the expansion rate of the universe, something we've been arguing about for years. There's a whole debate called the Hubble tension, the idea that our 2 best ways of measuring the universe's expansion rate give different answers. Some measurements suggest the universe is expanding faster than other measurements indicate. This discrepancy, if real, might indicate that our understanding of cosmology is incomplete. Lensed supernovae like SNSHP offer a third way to measure expansion, and Webb sensitivity makes it possible to catch them early, even when they're faint. The Hubble tension has been one of the most vexing problems in cosmology for the past decade. The cosmic microwave background, the afterglow of the Big Bang, provides a measurement of the current expansion rate of the universe. But this measurement is lower than measurements made by looking at distant supernovae and measuring their distances and redshifts. The discrepancy is significant enough that it can't easily be explained away as a measurement error. It suggests that something fundamental about our understanding of cosmology might be wrong. Perhaps the universe's expansion history is more complex than our current models assume. Perhaps dark energy, the mysterious driving the universe's acceleration, has properties we haven't yet recognized. Or perhaps there's some new physics operating at cosmological scales that we haven't yet incorporated into our models. The fact that lensed supernovae now provide a third, independent measurement of the expansion rate is therefore, if this third measurement agrees with one of the existing measurements, that helps resolve the tension. If it suggests a third value entirely, that indicates the problem is even deeper than we thought. So while it's out there spotting galaxies and black holes that shouldn't exist yet, it's also quietly helping to solve or complicate one of the biggest cosmological arguments we have. The very observations designed to answer one question end up generating new questions or casting light on entirely different problems. This is how science works at its best, with unexpected connections between different areas of investigation suddenly emerging as new data arrives. But then Webb found something even stranger. It started seeing galaxies that were no longer forming stars. Not millions of years into the universe's history, but within the first billion years. These weren't galaxies that were just starting to wake up. They were already quiet done, as if they'd been lit up briefly, burned fast, and then just stopped. That's not supposed to happen either. Galaxies are expected to go through a long, messy adolescence. Stars forming, dust flying, chaos all around. But these galaxies found just 700 million years after the Big Bang were already quiescent. That's the technical term. No new storming, no gas left to work with. It's like finding an elderly person in a kindergarten classroom. You don't expect to see someone that evolved that early. The discovery of these quiescent, or dead, galaxies in the early universe raised profound questions about how galaxies evolve. In the current universe, galaxies like the Milky Way are actively forming stars, though at a relatively modest rate. Older galaxies, more massive ones, have lower star formation rates than younger, smaller galaxies. But still, most galaxies are forming at least some new stars. The discovery of galaxies that had apparently shut down their star formation within the first billion years of the universe's existence suggested that under certain conditions, Galaxies could transition from active star formation to quiescence extremely rapidly. What would cause such a rapid shutdown? Perhaps an enormous burst of star formation early in the galaxy's life, consuming all available gas and triggering a supernova wind that blew the remaining gas out of the galaxy. Perhaps a supermassive black hole at the galaxy's center, activated and feeding, driving energetic jets that heat the surrounding gas and prevent further star formation. Perhaps a collision with another galaxy, disrupting the gravitational dynamics and settling everything into a configuration where star formation was suppressed. Whatever the cause, the fact that these galaxies had apparently undergone this transformation so quickly was surprising and fascinating. But Webb found them multiple times. They're now being called Sleeping Beauty galaxies. Catchy name, strange reality, because we still don't know why they stop so early or if they might wake up again. But it's clear that star formation, just like galaxy growth and black hole birth, doesn't follow one simple rule book. The universe of the early cosmos was evidently much more diverse in its behaviors and outcomes than previously appreciated. Different galaxies followed different evolutionary paths. Some grew rapidly through star formation and merger events. Others apparently experienced brief, intense star formation episodes followed by long periods of quiescence. Still others may have had their evolution shaped primarily by black hole activity. The diversity of outcomes suggested a cosmos far richer and more complex than simple models could capture. For a while, Webb's discoveries were all about what we didn't expect. Galaxies too soon, black holes too big, stars forming too fast, followed by rapid shutdowns and stellar death. But early 2025, something changed. The conversation shifted from structure and timing to life. The target was K2TPB, a planet about 120 light-years away, orbiting a cool dwarf star in the constellation Leo. We'd known about it for a few years. Other telescopes had picked up hints that it might have water vapor in its atmosphere. That alone made it interesting. Not Earth-like, but still in what's loosely called the habitable zone. Not too hot, not too cold, just maybe right. But Webb saw something more. In April 2025, scientists announced they had detected dimethyl sulfide, or DMS, in the planet's atmosphere. On Earth, this molecule is only produced by life, specifically by marine plankton. No volcanoes, no lightning, no chemistry we know of makes it without biology. However, scientists caution that unknown abiotic processes, for example photochemical reactions in hydrogen-rich atmospheres, could potentially produce DMS. Now it's important to be cautious here. This isn't confirmation of aliens. It's not proof of anything. The signal isn't strong enough yet to be called a detection beyond all doubt. But the odds, they're high enough to pay attention. Some estimates put the confidence around 99.7%. Not certainty, but not noise either. The implications of finding DMS in K2-ATT's atmosphere were electrifying. DMS is a smoking gun for biology on Earth. When marine organisms die and decompose, their sulfur-containing compounds are processed by bacteria, producing DMS as a byproduct. This gas is released into the atmosphere, and its presence in Earth's atmosphere is taken as evidence of biological activity. If the same molecule were present in the atmosphere of an exoplanet, it would suggest similar biological processes occurring there. However, wisely urged caution. The detection wasn't definitive. The signal was at the edge of what Webb could reliably measure. There were potential abiotic mechanisms that could produce DMS in certain atmospheric conditions. More observations were needed. More data had to be collected. But the fact that the signal was strong enough to warrant serious discussion was remarkable. It meant that, for the first time, we were beginning to ask real, testable questions about the possibility of life beyond Earth, based on actual observations rather than pure speculation. Webb didn't just pick up DMS. It also spotted methane, carbon dioxide, and hints of dimethyl disulfide, all molecules that in the right mix could point toward biological processes. And K218e isn't a gas giant. It's what we call a Hycean world, somewhere between a super-Earth and a mini-Neptune, a water-rich planet with a thick atmosphere, possibly with a global ocean under clouds. That combination, water, methane, CO2, and DMS, is strange. Not impossible in theory, but very unlikely without something living in the mix. A Hycean world with this particular mix of atmospheric gases would be a remarkable find if it genuinely harbored life. Unlike Earth, with its thin atmosphere and exposed rocky surface, K218b be completely covered by a global ocean beneath clouds, with a thick hydrogen-rich atmosphere above. Life in such an environment would necessarily be aquatic, perhaps microbial organisms inhabiting the ocean depths or surface, possibly biofilms or communities of microorganisms. The specifics remain speculative. The possibility was tantalizing. Of course, people debate it. They still are. Could photochemistry do this? Could there be some exotic process we don't understand yet, possibly? But that's what makes the observation important. It raises a real testable question, and it's the first time we've ever had that from a planet outside our solar system. No artist's impression, no theory, just data. And while the headlines ran with it, sign of life, the real value is quieter. Webb is finally giving us what we need. Clues, not stories. Signals, not speculation. The methodological shift represented by the K218t observations can't be overstated. For decades, the question of life beyond Earth had been pursued primarily through theoretical frameworks and abstract discussions of the chemical requirements for life. Astrobiologists would debate what conditions would be necessary for life to emerge and persist, and they would point to exoplanets that met those theoretical criteria as candidates for habitability. But without actual observations of exoplanet atmospheres, the discussion remained largely philosophical. Webb changed that. Now, for the first time, we could look at exoplanet atmospheres directly and search for the actual chemical signatures that would indicate biological activity. It was a fundamental change in how the question could be approached. But that wasn't the only milestone Webb crossed. In May 2025, astronomers confirmed the detection of the most distant galaxy ever seen, a compact bright object named MOOM 2C17. Its redshift was calculated at Z approximately 1444, meaning the light left Earth 3.5 billion years ago when the universe was 280 million years old. We're now looking at galaxies that existed when the cosmos was less than 2% of its current age. MOOM 2C14 isn't a massive system like the Milky Way. It's small, intense, bursting with star formation. Real, and it's not alone. Webb's deep field work has identified dozens of similar candidates, slowly filling in the blanks of a time we've never truly seen before. The observation of these extremely distant galaxies, with redshifts exceeding 13, was pushing us toward the edge of what Webb could observe. At such high redshifts, the universe was only a few 100 million years old. The light from these galaxies had been traveling for over 13.5 billion years to reach us. In a sense, we were looking back almost to the beginning of time itself, watching how the universe looked when it was in its infancy. Then came one of the strangest visual surprises in recent memory. In July 2025, the James Space Telescope captured an extraordinary image of two galaxies caught mid-collision, forming a system dubbed the Infinity Galaxy. When processed and sharpened, the combined shape resembled a near-perfect infinity symbol, a figure-8 twist of stars, gas, and gravity. Astronomers were captivated by its striking appearance, but the real story lay deeper. Now, yes, the shape got attention, it's striking, but the real story wasn't the symbol. It was what was hiding inside. At the heart of the collision between the two galactic nuclei, researchers identified a supermassive black hole actively feeding, pulling in material and building mass. Based on its brightness, energy output, and the extreme gas density of the collision, there's a compelling possibility that this is a direct collapse black hole, a rare phenomenon where a massive gas cloud collapses directly into a black hole without forming stars. This could be a critical clue to one of astrophysics' biggest mysteries: how supermassive black holes, from nothing to giants in a relatively short time. The Infinity Galaxy was particularly striking because it showcased multiple cosmic phenomena simultaneously in one visual snapshot. You had two galaxies in the process of distorting each other's shapes through gravitational interaction. You had a supermassive black hole at the center of this collision, actively feeding and powering a galactic nucleus. You had possibility that this black hole had formed through direct collapse, a mechanism not yet definitively confirmed through observation. The image was beautiful and scientifically rich, offering potential insights into multiple areas of astronomical study at once. It was precisely this kind of observation that made Webb so valuable. A single pointing, a single image, could reveal multiple layers of cosmic phenomena, each one worthy of detailed study and analysis. The Infinity Galaxy, observed about 7.5 billion years ago, when the universe was roughly 0.3 billion years old, isn't from the earliest cosmic epochs. But it offers a vivid snapshot of the chaotic mergers that shape galaxies and their central black holes. More than a stunning image, it serves as a laboratory for studying the processes that drive the formation of the universe's most massive objects, illuminating how collisions and extreme environments can spark the rapid growth of black holes. The processes occurring in the Infinity Galaxy likely were occurring throughout the early universe. Galaxy mergers would have been more frequent and more violent in the early cosmos when galaxies were closer together. Each merger would be an opportunity for central black holes to grow through direct feeding during the chaotic encounter. Multiple mergers over cosmic time could cause black holes to grow from modest sizes to supermassive ones. Observations like that of the Infinity Galaxy provide direct evidence that these processes were operating as theorists had predicted. We've been detecting exoplanets for nearly 3 decades now. And in all that time, we've mostly done it by inference, watching how starlight dims, shifts, or gets distorted by something passing in front of it. It's effective, but it's never really felt like seeing a planet. It's more like watching a shadow dance and trying to guess what cast it. So when the James Space Telescope captured its direct image of an exoplanet, it wasn't just a milestone. It was a moment of clarity. It happened in September 22. The planet TAPI 65466b hadn't even been the focus of any headlines before. One of the quieter targeting a faint star about 350 light-years away. Not habitable, just a massive gas giant several times the mass of Jupiter. The kind of planet that's easier to image because bright in the infrared and sits far enough from its star to not be drowned in glare. But that's exactly what made it the perfect test case. Using its coronagraph, a device designed to block out a star's blinding light, Webb was able to isolate the faint glow of the planet itself. Not a shadow, not a spectral trace, actual, coming from the planet's atmosphere, captured and analyzed in detail. The direct imaging of AC 652E6b was a watershed moment for exoplanet science. For nearly 30 years had it detected exoplanets through indirect methods. Now suddenly, they could see them. Not just detect them, but see them, look at them, study them as objects rather than as mathematical solutions to stellar motion data. Coronagraph aboard Webb was specifically designed for this purpose, blocking the overwhelming light of the host star, so that the much fainter light from an orbiting planet could be detected. In this case, HEB 65626b is a young exoplanet, still warm from its formation, radiating significant heat in the infrared. This made it an ideal target for Webb's infrared capabilities. The light revealed temperature, cloud composition, molecular fingerprints. It confirmed methane, detected water vapor, even suggested deeper structures in the cloud layers, things like pressure systems and haze. And for the first time, scientists could study a planet in another solar system as a world with its own visible character, not just a line on a graph. The ability to directly image exoplanets opens up entirely new avenues of research, whereas transit spectroscopy, the technique of analyzing starlight filtered through a planet's atmosphere, provides information about atmospheric composition. Direct imaging provides information about the planet's overall appearance, its thermal profile, the structure of its atmosphere. Different planets will have different characteristics, different cloud structures, different weather patterns. By directly imaging multiple exoplanets, astronomers can begin to understand the diversity of planetary atmospheres, the range of conditions that can occur in distant worlds. Of course, this kind of direct imaging isn't new in theory. A few ground-based telescopes have managed to do it in very specific conditions, but those images were noisy, barely enough to tell you what you were looking at. This one was different. This was clean, high resolution, detailed enough to break down what the atmosphere was doing, not just what it contained. It was the first time the distant glow of a world outside our solar system could be treated like real data, not a suggestion. And now that Webb has proven it can do that, the possibilities just opened up. Planets like HR 8799 Cyan, Beta Pictoris, and eventually the cooler ones, the ones we really want to understand, are now really slowly, carefully, for the first time, visibly. The population of exoplanets that Webb will be able to directly image is, for now, limited to young, massive planets orbiting nearby stars. These planets are warm enough and bright enough in the infrared that their light can be detected above the stellar glare. But as Webb continues to observe and as techniques are refined, the capabilities will expand. Eventually, Webb might be able to directly image Earth-sized planets around Sun-like stars, revealing their atmospheres and perhaps searching for signatures of habitability or even life. That's still far in the future, but it's now within the realm of possibility in ways it wasn't before Webb. And again, this wasn't hype. There was no big countdown, splashy press event. The data was released through peer-reviewed studies, and the simple carried all the weight of 2 decades of engineering behind it. This is how major progress happens now. Quiet, technical, measured, but undeniable. And while Webb was doing that, it also turned its attention to things much closer. Things flying through our own neighborhood. Asteroid 2024 OIR4. This was a near-Earth object about the size of a 15-story building. Not a headline grabber, not a threat, but still worth studying because small, fast-moving asteroids are hard to observe with traditional telescopes. They move quickly, reflect very little light, and often slip past with only a brief window of visibility. But Webb caught it, tracked it, measured the surface composition, determined its exact orbital characteristics. It even helped refine the risk models for the Moon, which had a probability impact window due to gravitational interactions. The study of near-Earth asteroids is not merely an academic exercise. These objects represent potential hazards, and understanding their properties, their orbits, their composition is crucial for planetary defense. If a large asteroid were ever on a collision course with Earth, we would need to know its properties to design a deflection strategy. Tracking and characterizing smaller asteroids like 2024 YR4, while they pose no immediate threat, provides valuable practice and builds our capability to handle larger threats should they emerge. Webb's ability to study such objects is therefore not just interesting from a scientific perspective, but has practical implications for planetary safety and security. It wasn't flashy, but it mattered because it showed that JWST isn't just good at looking into the past. It's good at looking around, at scanning the space near us with more detail than any telescope has ever had, even when the object is small, dim, and moving fast. And that's part of the real story here. Everyone thinks of Webb as the deep universe machine, and it is. But its infrared sensitivity, precision tracking, and spectral resolution have made it useful for everything from icy moons, dusty comets to active asteroids and beyond. It's not a one-trick telescope. It's a toolbox, and the things it's helping answer, from atmospheric chemistry to orbital dynamics, they're connected. Because if we want to understand how common Earth-like life may be, or how life could survive in harsh conditions, or what early planets even looked like, we need all of it. Not just the distant galaxies, not just the biosignatures, but the full picture from here to the edge of what we can see. The versatility of Webb was evident in the sheer range of science it was conducting. On any given day, it might be looking at distant quasars, then shifting focus to nearby exoplanets, then turning its gaze to objects in our solar system. The telescope was equally capable at all these tasks, addressing fundamental questions about the universe while simultaneously providing practical data about nearby hazards and resources. By now, it's obvious that James Webb isn't just another space telescope. It's not a sequel to Hubble. It's not a mirror in the sky that happens to see a bit further. It's something else entirely, something that's quietly reshaping how we understand the universe, not by screaming headlines or dramatic discoveries, by collecting the kind of data that changing over time. That change isn't always loud. Most of the time, it's just a shift in what questions we're even allowed to ask. Now, before Webb, we had guesses about the early universe. Now we have measurements. Before Webb, we could detect an exoplanet. Now we can describe it. Before Webb, we thought time. Now we've seen them form, burn out, and fade all within the first billion years. And that's the shift, not just in what we know, but in how we think about what's possible. The epistemological shift that Webb represents is profound. Science advances not just through the accumulation of knowledge, but through the ability to ask better questions. Before Webb, Questions about the early universe remained largely theoretical because we lacked the observational tools to address them empirically. We had models and predictions, but we couldn't actually look at the universe to see if our models were correct. Webb changed that. Now we can. We can look at the early universe directly. We can see galaxies, measure their properties, determine their distances and ages, and compare them to our predictions. When prediction and observation disagree, we learn something. We can refine our models, develop new theories, deepen our understanding, because what this telescope has shown over and over is that the universe evolves slowly and predictably. It evolved fast and sometimes violently. Galaxies grew faster than we thought they could. Black holes didn't wait their turn. Stars formed, burned out, and passed the torch long before we were supposed to be able to see them. And yet there they are, clear as day, sitting in Webb's data. So now we're left in an unusual place. A place where some of the biggest answers have raised even bigger questions. Why were so many galaxies already mature when they shouldn't have had time? How did black holes appear so early? Or what made them feed so fast? What kind of worlds are out there that could carry not just water and clouds, but chemicals we've only ever seen here on Earth? And maybe the most honest question of all, how much of our understanding was built on models that were just too neat, too slow, too simplified? These questions represent the frontier of modern astronomy and cosmology. They're the questions that will drive research for years to come. They're also uncomfortable questions in some ways. They suggest that our understanding of the universe has been incomplete. They suggest that the models we've built, while useful and mostly successful, are missing something important. That's not necessarily a bad thing. Science progresses by discovering the limits of current understanding and pushing beyond them. Webb is helping us do precisely that. It's showing us the universe as it actually is, not as our simplified models might suggest it should be. And the reality is far richer and more complex than the models. Webb isn't here to confirm what we thought. It's here to challenge it, to test it, to make sure we're not building stories that feel right, but ones that match what's actually out there. That's the core mission of science, really. Not to confirm our prejudices or validate our expectations, but how the universe actually works, regardless of whether that matches what we predicted. And it's still early. There are thousands of observations in the pipeline that haven't even been made public yet. Entire surveys that will run for years. Missions planned to pair Webb's results with new instruments, ones that will look in other wavelengths or catch up in resolution. And then there are the things we haven't even imagined yet. The surprises, the quiet anomalies, the strange patterns in background galaxies, the leftover questions from redshift measurements that don't quite align, the weird atmospheres, the gaps in stellar mass, the lensed flashes that might be something more. The future of astronomy in the Webb era is bright and of potential. New instruments are being developed that will complement Webb's observations. The next generation space telescope, when it eventually launches in the distant future, will observe at even shorter wavelengths, potentially seeing even more distant objects and finer details. Ground-based telescopes are becoming more powerful, using adaptive optics to correct for atmospheric distortion and reveal details that were previously invisible. These instruments will create a comprehensive picture at wavelengths and resolutions never before achieved. But Webb will continue to play a central role in this endeavor, providing data that informs the design and operation of future instruments. Because the thing about a telescope like this is you never really know what matters until you look. And when you finally do, it's never what you expect. No one knew Webb would find galaxies that shut down before they even got started. No one guessed we'd get hints of life from a planet 20 light years away this soon. No one expected such clear detail from the furthest galaxy ever seen to the class giant right next door. But that's what it's doing. Not once, not occasionally, but constantly. And in doing that, Webb has quietly shifted astronomy from a field on hopeful estimation to one grounded in evidence, detail, and sometimes uncomfortable clarity. It's not about pretty pictures. It's about finally seeing what's real. The philosophical implications of this shift are worth considering. For much of history, astronomy has been constrained by what we could observe. Telescopes grew more powerful, revealing finer details, pushing our vision further into space and back in time. But there were always limits. There were always objects too faint, too distant, too obscured by dust or glare to see. These limits meant that astronomy was always in some sense incomplete. We could see some parts of the universe in great detail, while other parts remained mysteries. Webb has expanded what we can see dramatically. It's pushed back the frontier of observability. But it hasn't eliminated the frontier. There remain epochs we can't see, questions we can't yet answer. But the frontier has moved. What seemed unreachable is now within grasp, and that changes everything about how we approach of the cosmos. The story of Webb's ultimately a story about human capability and curiosity. A team of thousands of people, working over decades, designed and built an instrument of extraordinary complexity and precision. They had to solve problems that had never been solved before. They had to innovate in countless ways, from the materials used to the software that controls it. And then the telescope finally launched, years behind schedule, and vastly over budget. It worked beautifully. And it's been rewarding us with discoveries ever since. The human achievement here is not just in the engineering, though that's impressive enough. It's in the vision, the idea that building such a tool was worthwhile, that the knowledge we would gain would justify the effort and expense. And it's been proven right many times over. And if this is what the first 3 years look like, the next decade isn't just exciting, it's going to change everything. We're only beginning to understand what Webb can tell us. The observations are still coming in. The analysis is ongoing. New discoveries are being made constantly. Some will be confirmed and will reshape our understanding. Some will be questioned and refined. Some will lead down dead ends. That's how science works. But the trajectory is clear. Webb has changed what we can observe. It's changed what questions we can ask. It's changed what kind of answers we can expect. The universe revealed by Webb is a universe far more active, far more complex, far more alive than we had appreciated. It's a universe galaxies form faster, where black holes appear earlier, where the first stars ignited sooner and burned brighter than we expected. It's a universe where worlds exist bearing signatures, hinting at the possibility of life beyond Earth. It's a universe that challenges our understanding at every turn and invites us to deepen our knowledge. And that's what makes it so thrilling. That's what makes Webb not just a telescope, but a window into reality itself.